Okay, welcome to video 8.3. Um, okay, so here's where we left off. So I gave these probability terms: probability, legendary eyesight, think tank J is this A plus BJ, E to the AJ, so on. Okay. um, is this identified? Once we write these probability terms in a likelihood function, will the likelihood function be identified? And it turns out it's not. By the way, this is very similar to a multinomial logit. In fact, it would be exactly a multinomial logit if it weren't for the CM terms. If those were X terms everywhere, we'd call it a multinomial logit, and that's how you could estimate it. So, given that one place where we're supposed to have an independent variable, we end up having instead a parameter to estimate. For that reason, it's not exactly a multinomial logit, but it's very similar. Now, one thing that happens in a multinomial logit is that one of the choices, they call it, so remember there's 200 think tanks. So one of the choices, you have to pick one of them. Well, and you have to set that parameter to something. So you have to pick one of the AJs and set one of them to something. Usually you set it to zero. Usually in multinomial logit you pick the first choice. So a sub one you set equal to zero, and usually you do b sub one equal to zero. You don't have to do it that way, but you got to pick one of the a's, set it to something. One of the b's, set it to something. Let me show you why that is true. Okay, so first, okay, I'm just going to rewrite this probability term, okay? But what I'm going to do is I'm going to add lambda to all the a's, okay? So this is where I'm going. I'm going to show you that if you add lambda to every one of the a's, then this probability term does not change. And it turns out this probability term does not change either. And for that reason, if that happened, then the likelihood function does not change, which means that you have an identification problem. Okay, so here's the idea. So probability J site. Oh wait, no, I legendary I sites J equals um, e to the, okay, now before I had a sub j here, but now I'm just going to add lambda to all the a's. So this means where I had a sub j here, but now I'm going to have lambda plus aj, okay, now plus b sub j times xi. And this is all divided by um, summation k equals 1 to 200 e to the now I would put a to the k, that's what I had before, but I've added lambda to all the a's. So now I'm going to have lambda plus a to the k plus b k x I. Okay. Now remember the rule from I think it's ninth grade math. So anything raised to the exponent. So e raised to the x plus y equals e to the x times e to the y. Okay. So what that means is we can rewrite this as e to the lambda times e to the a sub j plus b sub j xi. And then we can rewrite this term. Let's do the summation. K equals 1 to 200. Now, this term, we do the same thing. So this term equals e to the lambda times e to the a sub k plus b sub k times xi. Okay, now this e to the lambda this term doesn't depend on k, so we can move it outside the summation. Okay, and now what we have is e to the lambda divided by e to the lambda. Okay, so this is still the probability that I cites j. It's exactly what it equaled before. Okay, so if we add lambda to all the a sub j's, that probability term does not change. Now, to be careful, what I should have done, I'm going to also have this probability term in the likelihood function, but it's easy to show. The same thing happens here. You add lambda to all the a sub j's and a sub k's. That probability term is not going to change either. Okay. Okay. Now, so you got to set one. That means you got to set one of the a. We can't. Let's see. That says we can't identify all the a sub j's, but we can identify the difference between any two. Okay, but another way of saying that, one way to avoid that problem is to say you set one of them, one of the AJs equal to something. Then usually what you do is you set one of them equal to 0. Now it turns out it was useful to pick a think tank that had that was conservative, so that way it would have a low value in this exercise. It didn't really matter that much, but I wanted one that was cited a lot, that was convenient to do that, so I picked the Heritage Foundation. So Heritage Foundation, a sub heritage equals 0. Now, it wouldn't have mattered if I'd picked any other one. It would not have changed those probability terms. Okay, fortunately, you have enough in this class to understand that. Of course, once this is put on the blogs, you have these people who don't understand these methods, but they try to pretend like they do, and so all kinds of people are saying, "Oh, Grosclose rigged the results by setting the Heritage Foundation A." But maybe I shouldn't have done that. I should have said something else. But anyway, they're idiots out there. I shouldn't say idiots. The people who just don't understand these methods. But what they are is dishonest. That they don't understand the methods, and they try to pretend like they do. That's what I really dislike on those blogs. And there were some who did that. So, but anyway, you all know that it really wouldn't have mattered. Okay, you understand the math. How setting a different one of the A's would not have changed any of the results. Okay, now a similar problem exists with the B's. Okay, now let me show you. So let's look here. Okay, so here's another one. Probably I cites j. Same thing can happen. Let's add lambda to all the B sub j's. Okay, let's see what happens. Okay. So that term, probability I cites j, okay, it equals e to the a sub j plus, all right, now instead of b sub j, I'm going to write b sub j plus lambda times xi, all divided by summation k equals 1 to 200 e to the a sub k plus, now I'm adding lambda to all the b's, so we're going to add lambda to that b sub k. So b sub k plus lambda times x sub I. Okay. The numerator equals e to the a sub j plus b sub j xi plus lambda xi. Okay, and that equals, okay, we're going to use that same trick from our 9th grade math. E to the x plus e to the y equals e to the, e to the x plus y equals e to the x times e to the y. So what I'm going to do, this equals then I'm going to reverse them. Actually, I'm going to do 2 steps in one. So this equals e to the lambda xi times e to the a sub j plus b sub j times xi. So first I did is reverse the order. I said put that one first. And then once you do that, you get that term. Okay. Now, denominator equals e to the a sub k time plus b sub k xi plus lambda xi, and this k equals 1 to 200, and you're gonna get the same thing. So that equals summation k equals 1 to 200 e to the lambda xi times e to the a sub k plus b sub k xi. So now this term does not depend on k, so we can move it outside the summation sign. And so when we divide numerator denominator, we're going to have this term is going to, and this term are going to cancel. They're the same thing. Okay, and so you're going to get, that's the numerator, that's the denominator, exactly what you had before. Okay, and then, trust me on this, if we do the same thing here, or add lambda to all the b sub j's, you're going to get a similar term here. It's just going to be lambda times cm. Lambda times cm. They're going to cancel. And so this probability term is going to remain the same also. So if you add lambda to all the b sub j's, these probability terms won't change. Therefore, the likelihood function won't change. Therefore, you've got an identification problem with the b's too. So the way to solve that, you got to set one of the b's to something. Again, I picked the B for the Heritage Foundation, and that's very common with multinomial logit. You usually pick one of the choices, set the A, set all the parameters for that choice equal to 0. So A sub heritage and B sub heritage, both I set equal to 0. Okay, so that is an identification problem. You know what? I think I'm gonna stop there, and then I'm gonna write the likelihood function. Show maybe one more little possible identification problem. Okay, so see you there. This was 8.3. See you in 8.4.